everybody, it's Mrs. Harbin. We're talking about covalent bonding properties and dot structures. So I'm playing a little Jack Johnson. Hopefully you heard this song before. I might have played it before. Anyway, here's what we're going to be doing. Use electronegativity. Talk about covalent molecular compounds. Different kinds of bonds, resonance, and molecular structural formulas, and naming molecular compounds. A lot of stuff. So let's get going. Alright, please make sure to read these sections in the book and do these 3 problems. Okay, they're called self-check, and I gave you the page numbers. So do those. Alright, so basically, why do atoms bond? So we've been talking about valence shells, and the atoms that have full valence shells don't bond. So why do all the other atoms bond? To get full valence shells. So here's the valence shell of fluorine, outer electrons, 7 of them. So if fluorine shares with another fluorine atom, they each share their 2 of their outer electrons, or 1 each. Then fluorine now has 8 around it if you count the red and blue for that fluorine. That fluorine has 8 around it, so that's a full shell. Same thing kind of happens to make, so this is sharing electrons to get a full set. This is transferring electrons to get a full set. So the sodium atom transfers 1 outer electron to chlorine, and then sodium becomes a cation, and chlorine becomes an anion. But by doing that, they have a full outer set of electrons. So why do atoms bond? To get full valence shells. So what kind of bonding do they do? We're going to be talking about covalent for this chapter, but you still have to know them all. So what helps us predict? Electronegativity, the ability to pull electrons to make a bond. So if 2 atoms have no difference in electronegativity, they're nonpolar. So that bond is where electrons are shared equally, no poles or differences created. So how do we get this number? We take the electronegativity difference between the atoms. So we subtract electronegativity. Okay. Always do bigger minus smaller, get the absolute value. Okay. So if you subtract electronegativity and it's a small difference, they're going to be what we call nonpolar bonds. They're going to share equally. If you subtract electronegativity and get a medium difference between 0.5 and 1.9, then those elements will share electrons, but the higher electronegativity gets more of the shared paired. So there's poles created. So that's called a polar bond, right? But still sharing, okay? Keyword sharing. Right. Now, if the electronegativity difference is huge between the atoms involved, then like a 2.0 difference and up, then electrons can be transferred from the less electronegative atom to the more. Okay. So how do you get these numbers? Subtract electronegativities for the atoms in the bond. So just subtract one atom minus another, use the absolute value, and see if they're going to be sharing or transferring. Okay. So 0.4 or less, nonpolar, 0.5 to 2.0 polar, so these are the tweeners. This is equal or less than, this is greater or equal to. So what is NO? Well, NO is 3 minus 3.5, 0.5 difference, so that's polar. Okay, 3.5, what's the diff? 0.5, 0.5 is polar. Okay, F and F, well, 4 minus 4 is 0, so that's nonpolar. Okay, PB minus F, oh wait, PB's not even on here, F's here, so 4 minus PB, so we're going to go with ionic. I know the difference might be bigger than that, but this is a metal and a nonmetal. 2 nonmetals, look, on this side of the periodic table we have the nonmetals. They're most often going to be in covalent bonds, which are the sharing, covalent, sharing. Okay, C and H is C 2.5 and 2.1, 0.4. What's the diff? 0.4 difference, and that's nonpolar. Okay, so electronegativity helps us decide what atoms are going to do with their electrons. Covalent share. Oh, they're sharing electrons. What kind of atoms do that? Atoms that are similar in electronegativity. Nonmetals. It's called directional covalent bonds because those electrons are shared between the atoms. They're not shared by everybody in a whole array of atoms. It's just right stuck in between, constantly in motion of course, but in between the nuclei of the atoms. Why do they share? To fill octets. That's 8 is great. Octet rule to get a full shell, which is usually 8 electrons. Shared electrons count for each atom. NH3 shares electrons. I'll show you what the molecule might look like. And so these electrons that hydrogen has are shared with those electrons that nitrogen has. Okay, nonpolar covalent bonds is when you have 2 nonmetals that share pretty evenly. Okay, what kind of substances do that? Diatomic elements. I'll talk about it a little bit later, but remember this. Naf, cool, br, e. All right, remember that. What do nonpolar covalent bonds usually cause? Low boiling points and melting points. They don't conduct electricity, they don't really conduct heat, and they don't dissolve in water. So, oh, look at that's pretty equal sharing between those two little creatures. All right, polar covalent bonds. The one that's more electronegative pulls the electrons closer to its nucleus, so there's uneven sharing. Higher electronegativity has kind of a negative charge. The other one will have a slight positive charge. That creates what we call a dipole. Say that word, dipole, 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 dipole. Okay, it's when there's uneven distribution of electrons. So we use this delta sign, okay, that's that, to represent the partial charge on each molecule. The delta negative, or that symbol, this is on the negative side, or that points to the negative side of the molecule, okay, or the bond. And things that have polar covalent bonds might dissolve in water. What's an NO bond? Well, N is 3.0. We just saw from the electronegativity. Oxygen is 3.5. So what's the diff? 0.5. So an NO bond would be polar. How do we indicate a polar bond? Well, we point an arrow to the side of the bond that has the higher electronegativity. That means the other side of the bond is kind of positive. Or you use the deltas. Delta positive on that side of the bond, delta negative. That's for polar bonds only. Why? Because they have uneven sharing. Okay, how do we represent these molecules where these electrons are being shared? There's two kinds of formulas. I'm underlining two special names. Structural shows you how the atoms are connected. Okay, how the atoms are connected. So both of these are structural. Molecular counts the atoms. 1, 2 carbons. 1, 2 oxygens. Oh, well, 1, 2, 3, 4 hydrogens. And 1, 2 oxygens. So this is molecular because it counts the atoms. Okay, C2H6. Count them, count them, count them. Molecular. All right. Show how they're arranged. Structure shows arrangement. Okay. All right. So match them up. Let's see. Molecular, structural. Molecular, structural. Molecular, structural. Molecular, structural. So maybe wondering, how do we get these structural formulas? Well, how do you get a molecular formula? You count, all right? 2 H's, 2 O's. Hydrogen peroxide. 2 C's, 6 H's, 1 O. That's ethanol, okay? Structural, molecular, structural, molecular. Okay, naming molecules. All right, we're only going to name the molecules that have 2 nonmetals in them, because the other ones are a little bit different, okay? So in order to tell you how many atoms of each kind, you have to know these prefixes. These prefixes are only used for molecular compounds. Mono means 1, di means 2, tri means 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, deca 10, okay? Get to know these prefixes. We need a prefix for the 2 atoms in the molecule to tell you how many there are. And the second word is going to end in IDE because it sounds good. So let's practice. All right, I know this is a molecular compound. How do I do? No, nonmetal, nonmetal. So I need to tell me how many sulfurs there are. There's only 1 sulfur. So you're probably thinking put monosulfur. The only time you can skip a prefix is no mono on the first. So no mono on sulfur because it's the first atom. But we have 6 F's. So that's hexa for 6. For, and not ene because you ended in IDE. Okay, second word is IDE. This is phosphorus. Phosphorus. Do I need phosphorus? Phosphorus. How many chlorines? 5. Penta. And then chloride because you end in IDE. Okay, 2 xenons. Di-xenon. 8 bromines. Octa bromide. All right, I ended in IDE. Dihydrogen. Now I do need a prefix for a second every time. That's mon. Oxide, you don't put monooxide, it's just monoxide. Hey, that looks like water. All right, trinitrogen. N for nitrogen, tri 3. Monosulfide means 1S. And ide is the end of the word. Hexasulfur, S6, dichloride, Cl2. Prefix, how many? All right. Decanitrogen, N10. Monoxide O, N10O. All right. So you always need a prefix on the second. IDE on the end. Prefix on the first unless it's mono. We'll keep practicing. It says let CO be your guide. This is carbon monoxide. So it has all the rules in it. No prefix on the first. Definitely prefix on the second. IDE for the end of it. And don't breathe it in. Okay, electron dot diagrams. How can we draw some of those things that I was showing you earlier? They help us picture atoms and ions, okay? So you find the atom that you're talking about on the periodic table and write down the symbol and then use dots for valence electrons like so. All right, so nitrogen. I'm finding on the periodic table, I know it has 5 valence electrons because it's in group 5A. So I put the dots around 1, 2, 3, 4, 5. All right, so each valence electron becomes a dot and you double up once each side is full. Okay, hey, look, it's a bunch of Lewis dots. All right, how did they get this one? 2A, 2 valence electrons. Magnesium, 1 dot, 2 dot. Could I have gone magnesium, 1 dot, 2 dot? You betcha. Okay, this is group 7A, 7 valence electrons. Fluorine, 1, whoopsie. We should go around first. I mean, you'll find out after a while. Okay, 7 valence electrons. So how do you know how many bonds these atoms are going to make? Well, single dot means a bonding site. Okay, single dots mean bonding site. So count the single dots. Example, hydrogen. 1 single dot, it's going to make 1 bond. Fluorine, 1 single dot, it's going to make 1 bond. Nitrogen, 1, 2, 3 single dots, 3 bonds. Now, that's likely. All these elements up here, okay, period 1 and 2, can only make 8 bonds total. And some of them can't even do that. All right, but then if you get some of these bigger elements, they can expand and go more than 8, so they can go higher than an octet. Okay, there's 7 diatomic elements. I wrote this early, Nonpolar NOFCl, Bri, and H are the 7 diatomic elements. Where are they on the periodic table? Well, it starts with number 7 and makes a 7, but then that 7 points over to hydrogen. 7 elements. What does it mean to be diatomic? Di, 2 atomic atoms. So nitrogen will never hang out by itself when it's an element. It always hangs out with itself when it's an element. Oxygen will always hang out as O2. Remember this word, Nonpolar. If it's one of those and it's by itself, meaning not bonded with another kind of element, it'll always be diatomic. All right. So I thought that Nonpolar was a funny word. So cattywampus is a funny word too, and here's what it means. Okay. Lewis dot structure. So we go from an atom where you can see how many bonds it's going to make and how many valence electrons it has to a compound or a molecule, okay, which is still an element but a molecule. So let's do some. Find the one that can make the most bonds. So carbon can make 4 bonds. I'm going to put that in the middle of my molecule, and there's 4 hydrogens. Each hydrogen can make 1 bond, so I'm going to put that on the outside. H, it's got its 1 valence electron. H, that's across, 1 valence electron. All right, so then every time 2 electrons make a bond, you can erase the electrons and boom, boom, draw a line to show a bond. Okay, a line means a bond, a single bond, 2 electrons right there. So now carbon has 2, 4, 6, 8 around it. This hydrogen has 2, that hydrogen has 2, that hydrogen has 2. But wait, 8's the magic number. Except that hydrogen only needs 2 electrons to be stable like helium. So hydrogen stops after it makes a single bond, it's done. NH4 positive. Uh-oh, ion. What does positive mean? 1 less electron. So I have nitrogen and I have hydrogen. I'm putting nitrogen in the middle because it makes the most bonds. All right. And then I only have 4 electrons from hydrogen, 1 from each. 5 electrons from nitrogen because it brings in 5 plus equals 9 valence electrons. But 1 has got lost. Minus 1 equals 8 valence electrons. Okay. So each hydrogen... Nitrogen used to have 5, but now it only has 4 because it lost 1. And then we could draw the lines. Okay, so every time there's a bond, it's a line of which represents 2 electrons. Okay, and then overall, this has a positive charge. Okay, we'll talk about what that means later. PCl5, phosphorus, 1, 2, 3, 4, 5. Chlorine, 1, 2, 3, 4, 5, 6, 7. Chlorine can make 1 bond. Phosphorus looks like it can make 3. There are 5 chlorines. Since phosphorus is in the third period on the periodic table, it could expand, and instead of needing an octet to be happy or stable, it can go up to 10, up to 10 to 12 electrons. So chlorine has 7 around it. That chlorine has 7. This chlorine has 7. I'll put another chlorine here. The atom that can make the most bonds goes in the middle. And then every time two dots makes a line, there's a bond, a bond, a bond. Okay. So this is how PCl5 forms. Okay, I'm going to skip NCl3 and do N2. 2, 3, 4, 5. Nitrogen, 1, 2, 3, 4, 5. 2 Ns. All right, make a bond. Okay, you think you might be done, but look, 1, 2, 3, 4, 5, 6. Nitrogen only has 6 around, needs 8. All right, I ran out of dots. I can't put any more dots because nitrogen only brings 5. So I can start sharing more than 2. So now they're sharing 4. 1, 2, 3, 4, 5, 6, 7. Still not stable. So I have to share even more. And now 2, 4, 6, 8 for nitrogen. 2, 4, 6, 8 for nitrogen. This is called a triple bond. Okay, so resonance. So if I put nitrogen in the middle, because it can make 3 bonds, all right, put oxygen around the outside. Nitrogen brings in 5 electrons. Oxygen brings in 6 electrons, and there's 3 oxygens, so we're at 18 plus 5 equals 23 plus a negative charge plus 1 more. So where am I getting this number? What does this number mean? 24 dots, 24 electrons. All right, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, 26. Oh, wait. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 total electrons. So it looks like I'm done, right? I just need to put this on the outside because it's negative. But wait, nitrogen does not have an octet, and it always needs an octet. So then oxygen can go ahead and share that pair with nitrogen. And so now nitrogen has 2, 4, 6, 8. It's appreciating oxygen there. And this oxygen is 2, 4, 6, 8. But wait, why couldn't I put that double bond on that side? Or, whoa, lots of dots, all right? Or, why couldn't I put that double bond at the bottom? And the truth is that all of these dot structures, all 3 of these dot structures, work equally well to represent NO3-, but none of them represent the reality of NO3-. So we call these, when you could have equal structures that represent a molecule, we call them resonance structures. And that's what that means. Uh-oh, the bell's ringing. I got to go to class. So I'm going to move on. Not all bonds are single bonds. We saw if they're sharing 4 electrons, it's a double bond. If they're sharing 6 electrons, it's a triple bond. Okay? So make sure you know that you can have double and triple bonds. If you could see something that's covalently bonded, you're going to want to look for these characteristics. All right, nonmetals, sharing electrons, don't conduct electricity. We'll test in the lab to see these things. Okay, you should write them down. Remember to do this from the book. All right, this will help you with dot structures. So this is a sharing song from Jack Johnson. And then it's all about, I think I might have played this before. Anyway, peace out. See you later, Harbs.